Okay, yesterday we were working on finding some extreme values. So let me just put this aside. So extreme, it's also called extrema values of a function. So it's pretty straightforward. It's either going to be the maximum or the minimum y value for a certain interval of x. So between the x values of a and b, for a certain function, what is the maximum or the minimum y value? So let me show you some cases here. I think there was a good diagram here. So one of the points where this happens, where extrema values occur, is at horizontal tangent slope lines. So over here, the slope is 0. Over here, the slope is 0. There's a turning point. At a turning point, usually you can get your maximum or the minimum values, which is what this first diagram is. Both the max and the minimum are at turning points. Makes sense. In the second diagram, the maximum is at a turning point. The minimum, however, is not. Although there is a 0 slope here between this interval, that is not our minimum value. Our minimum value is actually something else. So it doesn't automatically mean that the horizontal tangent lines are automatically min or max. In the case 3 is that neither max nor min are actually part of the turning point. Although there's 0 slopes here, neither one of them are extreme values. So that's point number 1. You have to check. Essentially what you do is once you find this tangent slope is 0, you have to check y values for the other x values in your x value range. Also going to quickly discuss the idea of a local extrema versus absolute extrema. And I can remember extrema just means minimum or maximum values. So here, let's take a look at this case. So let's say you have a quadratic. Let's say you have a point. Let's say this is 1, 1. Doesn't matter what it is. Is there any other point on this curve that will give us another maxima or minima? Another extrema is what I meant. What do you think? We have a vertex here. Do we have any other extremas? So the answer to that question is that no. We have a vertex. This right here, there's no other point that will go below this. This is called the absolute minimum. Because in this function, you'll never have a y value less than 1. That's the vertex. Now compare this with something like this. We have a cubic function. We have a maximum here and a minimum here. Are these locals or absolutes? So these are locals because this y value here is higher than the max, right?
Mm-hmm.
And this y value down here is lower than the min. So this and these are called local extremas. Because in the function, we have higher y values and lower y values. Whereas this one right here is the absolute minimum. There's no other y value that would occur. For this, there is no absolute maximum. Absolute maximum doesn't occur because these y values will go on forever till infinity. So that's the idea of extremas. Let's do a few problems. We did some yesterday. We will just pick it up right there. Let's look at this graph here. This one says, state the absolute maximum value and the absolute minimum value of each of these functions. So it's on a closed interval, so it's not going to go on till infinity. So these definitely have an absolute value. It's very simple. Look at this. This is your absolute max. This is your absolute min. This is your absolute max. This is your absolute min. The lowest possible value there, right? This is the same thing as B. C is the same thing as B. Here's your minimum. Here's your maximum. And both of these are absolutes because there's no other y value on this graph that's higher or lower than these points. And finally for D, again, it's very simple. Right here is the maximum and the minimum is right here, -20. So from a graph, it's very, very easy to see. But the issue is we won't be able to graph it every single time. Well, this one is outright telling us to sketch it out. So this one, we don't have a choice. We have to sketch it out. It says find the extreme, absolute extremas. So we don't care about locals. We're only looking for the absolutes. What kind of a function do we have here?
Polynomial.
A polynomial function. It's a cubic function, positive leading coefficient. Which axis does it start? Where does it end? Starts here, ends there, okay?
Mm-hmm.
I'm thinking how to factor this, because if we have to graph this, all right, so before we can graph it, we have to factor it, which doesn't look like it's super easy here. Usually what happens is that one of the factors of this polynomial will be a factor of this leading coefficient here of 1. But doesn't look like this one is going to work out that way. So what we do know for this function is that it starts down here, it ends up here. Y-intercept is +1. We don't know where the x-intercepts are. Yeah, we don't know where the x-intercepts are, which is fine. So let's see if we can pinpoint where the turning points are. How do we find the turning points? What happens here?
The slope is 0.
The slope is 0. So we're going to find f prime of x, which is very simple for this. 6x squared minus 6x minus 12. And we're going to set it equal to 0. And we will get 2 different turning points. Here you can pull out a 6x. If you can pull something out, always pull something out. So we can't pull out a 6x, we can pull out a 6. X squared minus x minus 2. Two numbers that multiply to -2 and add to -1. What are they? -2 and +1. Okay, like that.
Mm-hmm.
So where are the two x, or not the x-intercepts, rather the turning points? One of them is at 2, one of them is at -1. So right here we have this, right here we have this turning point. Now what I'm going to do is, this is not part of our domain. Actually it is, sorry. -2 to 0. This is not part of our domain. 2 is more than 0, so we don't care about this. So we don't really care about what happens after this point. -2 to 0, sorry, after this point, we don't really care. We don't care about the other turning point. We only care about this turning point. So at -1, let's find the y value. F of -1 is -2 minus 3 plus 12 plus 1. That's 13 minus 5, that's an 8. So this y value is an 8. Is that a minimum or a maximum?
maximum.
A maximum. So right now we're looking at it from -2 to 0. So we're only interested in this box, this little box that we have. And in this box, we know at -1 there's a turning point, and we know that's going to be our absolute max. What about the absolute min? Where does it look like it is? Is it at -2 or 0?
0.
0, and that's the answer to this question. But what happens usually is that you can't graph it. Let's look at this question. Or it's not as easy to graph it, like this one. What kind of a function do we have here? What's the name of this? It's not a polynomial. It's a rational function. If it has a numerator and a denominator, it's a rational function. And if there was no x there, you could say that this is a reciprocal function. But since you have a function over a function, not a number over a function, this you can say it's a rational function. And graphing rational functions is not that easy. We could try. Yeah, let's try it. Is there any x values that this cannot take? Is there any value of x that would make the denominator a 0?
1.
No. If x is 1 or -1, you would get a denominator of 2. See if you agree with that. There is no value of x that would give you a vertical asymptote, or that would make this function moot, right?
Mm-hmm.
Basically what you're doing is there any value of x that will give me a 0 in the denominator? You have x squared equals -1. You can't really take the square root of -1. You can in a different number system, but we don't use it. It's I. Square root of -1 is called the imaginary number I. I equals square root of -1. We don't use this. Not for this course anyways, maybe later down. So there is no value of x that would make this function moot or undefined. So that means it doesn't have any vertical asymptotes. What about horizontal asymptotes? So vertical asymptote doesn't exist. Horizontal asymptote does exist. We've talked about this before months ago. For a rational function, okay, there's 3 cases. It's all about the degrees. If your degree in the numerator is less than the degree in the denominator, you have a horizontal asymptote at y equals 0. Is that the case here? What's the degree in the numerator? What's the degree in the denominator?
It's less than the denominator.
Yeah, it's less than the denominator, so we have a horizontal asymptote here. So now that's sorted. Always for a rational function, you're gonna find the VA, vertical asymptote, which is what makes the function undefined or gives you a 0 in the denominator. The next thing is horizontal asymptote, and this is how it works. This is gonna be the case most of the time. Next, we're gonna need our x-intercept and our y-intercept. How do you find the y-intercept? It's easy here. What's the y-intercept? 0 or 1?
1.
0. Y-intercept is when x is 0. So when you set, because the numerator will give you a 0 here. It'll look like this. You'll get 0 over 1. It'll be 0. So the y-intercept is at 0. If the y-intercept is at 0, the x-intercept is automatically at 0. So we know this function passes through the origin. That is what we know. Next, we're going to plug in these two values. F of -2 is going to be -8 over 5, so that's negative 1.6. At negative 2, we have negative 1, negative 1.6. That's what we have. What about at 4? Again, we're going to do the same thing. At 4, it's going to be 16 over 17. It's almost 1. Almost 1. 1, 2, 3, 4. Over here, the y value is almost 1. So that is what we have. Good so far?
Mm-hmm.
So our function, right? Did we do n behaviors? I think we did. Anyways, for this function, because there's a horizontal asymptote here, there's a point here. It cannot cross the horizontal asymptote unless it's through an intercept. So this must come from here. Or you can even think of it this way, okay? How did I get these points? Like, you may not know how I got these. What we do is we're gonna plug in, so this is called n behaviors. We wanna know where this function is coming from. You just plug a very large negative x value in here. So if I plug f of negative 10,000, I will get something close to 0. If I plug f of positive 10,000 in this function, I know this is going to be close to 0 because this is going to increase way quicker than x. So eventually the denominator will be much, much bigger than the numerator for as x becomes larger and larger and larger. So you can try plugging in a big negative x value and a big positive y value. You'll see that both of them are close to 0. That means this function would look something like this. It's going to come right here. It's going to come, go through here. There has to be a turning point somewhere. Goes through here, and again, it's going to come down to 0. So that is what it would look like. Is this making sense?
Mm-hmm.
Now our goal is to find, again, we don't care about negative. This is just to show you how to graph it. We don't care about anything less than negative 2 and anything more than positive 4. We don't care about any of this. So now what this is our box that we're looking at, secluded, isolated box. Looks like there is a turning point here and potentially a turning point up there. How do we find the turning points?
You find when the slope is 0.
You find the slope is 0. So f prime of x. What's the derivative of this? You have to use the quotient rule. Remember quotient rule? F, this is g, f prime g minus f g prime all over g squared. So what's the derivative of this?
4 times x squared plus 1
Yeah,
minus 2x times 4x.
yep. And then you get this in the denominator, g squared. And we're looking for the turning point, so we're going to set our derivative function equal to 0. And this looks difficult, but it's not. It's just a quadratic function. Look at this. We're going to multiply both sides by the denominator. What's going to happen to this denominator when we multiply both sides?
It's gonna just go away.
As it's just going to go away. See you later. So we just have a quadratic. Quadratic is pretty easy. 4x squared plus 4 minus 8x squared. So we have negative 4x squared plus 4. Negative 4x squared equals negative 4. Negative signs cancel out. X squared equals 1. If x squared is 1, what's the value of x?
It's 1.
There's 2. Remember plus minus, okay, at this level,
Mm-hmm.
square root of anything is gonna be plus minus when you're solving an equation. X is gonna be plus or minus 1. So now we've pinpointed where these extreme values are. At 1, there's a turning point. So right here, and at -1, there's a turning point. Now for the final step, this is what we're gonna do. Did I find f of 2 before? I think I did. F of 4 was close to 1. I found this before. F of -2 was, I think, 1.6, -1.6. Now what we're gonna do is we're gonna find f of +1, which will be 4 over 5, that's 0.8. And we're gonna find f of -1, which will be -4 over 2, -2. So now we can draw precisely where everything is. At 4, it's close to 1, not exactly 1. At +1, it's 0.8. At -1, it's -2. And at -2, it's -1.6. So it looks like we have our maximum from this diagram anyways is right here. Because this was close to 1, this one is 0.8, so that's going to be our maximum. And this is going to be our minimum. Okay?
Mm-hmm.
And that's it. So that's how you can get something like this, even if you can't graph it. Let's try an A problem. So swimming pool is treated, usually done with chlorine, which is not that good for your skin or eyes, but it's the best thing we have. Yeah. Suppose that T days after treatment, the number of bacteria per cubic centimeter is this. So we're given a count of bacteria. Determine the lowest number of bacteria during the first week after the treatment. So we have a quadratic function that models the population of bacteria in a swimming pool, where t is the x value and nt is the y value. Determine the lowest number of bacteria. So we want to minimize, we want to find the lowest y value for this function. What's our approach? It's a quadratic. Is it opening up or down?
Up.
Up. We know the y-intercept, 500. We don't know where the vertex is, but what happens at the vertex?
The slope is 0.
The slope is 0. So if we find this, that's going to be our lowest y value. Agree with that?
Mm-hmm.
So we just need to find what is this x value here. And what is this y value? We just need to find the vertex of a quadratic. How do we do that? Vertex of a quadratic. No? You find the x-intercepts, you find the middle of the x-intercepts, that'll give you the vertex. Okay? That's one way.
Mm-hmm.
Actually, I'm just gonna show it to you, because why not? So we're just gonna go off on a tangent here. Finding the x-intercepts, not the x-intercept, finding the vertex. I'm gonna show you, I think I've done this before as well. I'm gonna show you every method I know on how to find the vertex of a quadratic. Mathematically, it's not that difficult. You just need to remember the steps. So this is our function. We need to know, where's the vertex? Now, the x-intercept method doesn't work if it doesn't have any x-intercepts. Remember that? If it doesn't have,
Mm-hmm.
because the vertex is in the middle of the two x-intercepts. So if it doesn't have an x-intercept, it is not going to work. So let's first check whether it has an x-intercept. So we're going to check, does it have x-intercept? Does it even have x-intercepts? We're going to compare this with the general quadratic formula. Ax squared plus bx plus c. Can you tell me what a, b, and c are?
30 minus 240 and 500.
And 500. So this is how you check whether something has x squared or not. This comes from the quadratic formula. This is part of the quadratic formula. If you're b squared minus 4ac, if this is less than 0, no x-intercepts. If it is greater than 0, 2 x-intercepts. 2 x-intercepts. And if it is exactly 0, then it just has one repeating x-intercept. There's a turning point, which means there's a turning point at the x-intercept itself. So we just have to check for this. So let's do it. So we have 240 squared minus 4 times 500 times 30. Yeah,
Mm-hmm.
let me plug this in. 240 squared minus 500 times 30 times 4. I get negative 2400. So what does that mean? How many
There's no
x-intercepts?
x-intercept.
There is no x-intercept. So now we've hit a wall. How do we find the vertex of something that doesn't have an x-intercept? Or this method is not going to work. The finding the HK method, first finding the x-intercepts, finding the midpoint, which is H, K method failed. Does not work here because it doesn't even have x-intercepts. So now we have to think of it a different way. And here's how you want to think of it. Remember, vertex is always H comma K. H is always negative b over 2a. And to find k, you just plug the h value back in the function. So this is bulletproof. This one, we don't care about x-intercepts. So, and I'll show you a third way, which is the easiest way later. So let's try this, see if we can figure this out. So minus b, so that'll be 240 over 2a, so that's 2 times 30. 240 over 60, that's a 4. So the x-intercept is at the x value of 4. To find the y value, we're going to plug 4 in there. That's going to be 30 times 4 squared minus 240 times 4 plus 500. I got 20. So that point is 4 comma 20 using this method. Cool?
Mm-hmm.
Here's a third method, which is the best way. We're going to find the derivative. We're going to find n prime of t and set it equal to 0. N prime of t gives us the slope function, and we know at this point the slope function is 0. The slope is 0. So when we solve this, we will get the x value, which we know is 4. What's the derivative of this function that we have?
-62 minus 240.
Solve this for t. You get 240 over 60, 4. Plug this back in there. The y value, n of 4, already found it down here somewhere, 20. There we go. This is the easiest way. This method works for any function, whereas obviously this is only for quadratic, only for x squared. It doesn't work for anything else, this vertex method. Whereas this setting the derivative equal to 0 method works for any function, okay? So therefore the answer to this question is after 4 days, bacteria count is gonna be 20 per cubic centimeter. That's the end of the answer. All right, let's move away from this a little bit. See if there's anything different. No. All of these, you just find the first derivative, set it equal to 0, and you should be good. Should we do one? Doesn't have any of the A symbols. Maybe this one's worth doing. We'll just do it. Why not? We're given a function. How would you describe this function? Is it a polynomial?
No.
No, it's a root function because you have the 7th root of 3, whatever, x cubed. So yeah, this is going to be a root function. Which is, again, not the easiest to graph, so we're not even going to bother. The forward motion, t seconds after touchdown, is described by 189t minus t7 over 3. What is the velocity of the shuttle at touchdown? We are given a displacement function, okay? How do we get the velocity from a displacement function?
You find the first derivative.
You find the first derivative. So what will be the first derivative of this function? Here, let me show you what's actually happening in this question. I guess context is a little bit important. You have a space shuttle, and don't mind the drawing. Probably has like a giant rocket pack attacked. You have this thing. It's coming down. It has a nose gear, landing gear. It has all this thing. Here's the runway. Space shuttle is a modified airplane in a way, okay?
Mm-hmm.
Um, it's gonna land here. What's the time when it lands? When it touches the ground, what's the time right now? 0. The time, the moment it touches the ground, is exactly 0. Because this function models the motion after its touchdown. So the moment it touches down, time is 0. And then this thing is going to bounce up, right? It's going to be put and then it's going to go straight up like that. No touchdown is perfect on the first try. So it's going to do something like this, like a dampening motion. And this motion is described by this graph, which is, again, not going to be the easiest to graph, but it doesn't matter. We don't need the graph. So that's the context of the question. Part A is asking us for the velocity at touchdown. So we need to find s prime of t at what time?
0.
0. So this will be, first, let's find s prime of t. It'll be 189 minus 7 over 3 times t to the 7 minus 7 over 3 minus 1 is 7 minus 3 over 3. That's going to be 4 over 3. That's the thingamajig. And we're going to set this as 0. So it's going to be 189. What's the unit? Remember, it's the slope. The slope of the distance or displacement function. Seconds is the x-axis run. On the y-axis, we have height in meters.
Meters over second.
Meters per seconds. Done. B. How much time is required for the shuttle to stop completely? So we have the velocity function. Vt is 189 minus 7 over 3 t4 over 3. What's the velocity when something stops? Is it going to be moving? It's going to be 0, yeah. Then we're going to solve this for t. So it'll be 7 over 3 t to the 4/3 equals 189. And there's a negative here, the negatives cancel out. How do we solve this for t?
You divide by 7 over 3.
Okay, so let's get rid of the 7 over 3. What's next? No? Would this help? How would we get rid of that 4th root there?
You do to the power of 4.
You do the power of 4 on both sides. So power of 4, power of 4. Boom, boom, gone. How would we get rid of the t cubed there?
You cube root.
You cube root it. So I'm gonna cheat a little bit. I'm gonna first cube root, because remember, exponents, you can do this in any order you want. So instead of doing power 4 and then cube rooting it, I'm gonna first cube root and then do power 4. So or actually, no, that doesn't work. I thought cube root of 81 was 3, but it's the 4th root that's 3. Okay, I'm gonna have to use a calculator here then. So to the power 1/3. Let me just double check the math. Yeah, so it takes 350 seconds. Cool.
Mm-hmm.
Part C, how far does the space shuttle travel to a complete stop? So we know it takes 350 seconds for it to stop. What is part C asking us? Is it S prime of 350? S of 350? What is it asking us?
S of 350.
Yeah. So we're going to plug 350 in here and in here. So S of 350 was going to give us the distance it travels. So 189 times 350 minus 350 to the power of 7 divided by 3. So what did I do? I did something. 189 times 350 minus 350 squared. I got a negative number. Why did I get a negative number? I think this time is wrong. Let's try redoing this again. Because that's a long time, right? What's 350 seconds in terms of minutes? How many minutes is that? Approximately how many minutes is 350 seconds? It's 6 minutes. Yeah? 60 seconds in a minute. 360 seconds would be 6 minutes. So it's almost 6 minutes. The derivative of this is 189 minus 7 over 3 times t to the power 7 divided by 3 minus 1 is 4 over 3, right? Yeah. So let me see what went wrong there, if anything. So this is 7 over 3 t to the 4/3 equals 189. 189 times 3 divided by 7 is 81. So this is, okay, I see what I did wrong. This is 81. So I'm going to rewrite this as this. We need to get rid of this cube, so I need to cube this first, and then I take the 4th root. I did the other way around. I did the 4th power, 3rd root. So power 3, and then we take to the power 4th power. So t is exactly 27 seconds. That makes way more sense. So t is 27, so we need to find s of 27 for part C. Because I got a negative distance, so it doesn't make sense to me that the space shuttle touched down this way and then somehow ended up over there. That makes no sense. So I knew something was wrong. S of 27, so let's plug 27 in there. This should give us a nice number, minus 27 to the power 7 over 3. Gives us 2916 meters, which is perfect. A runway is about 5 to 8 kilometers long, so 3 kilometers is perfect. So that's the answer to part C. So it helps sometimes, especially in application type problems like these, to have a hypothesis. And this doesn't apply to just to maths. This can be for anything. If you have an idea of what number you're expecting, like for here, this distance, I was definitely expecting a couple thousand, or at least a positive number. So the fact that I got a negative number means something went wrong. And what went wrong was I flipped this. I did this and this when it should have been like the way it looks. Part D, what's the deceleration after 8 seconds? So I'll give you a hint for that. It's asking us for the acceleration after 8 seconds. Deceleration just means it's going to be negative. So this is our velocity function. It's asking us to find the acceleration after 8 seconds. What are we looking for? How do you get acceleration from velocity?
You find the derivative.
You find the derivative. So you find a of t, which is v prime of t, the derivative of the velocity function, or the second derivative of the position function, s double prime of t. What will be the derivative of this thing?
4/3t to the power of 1/3.
Good try, but you're missing the front chunk. So 189 is 0, negative 7 over 3 times 4 over 3, and then t to the power of 1/3, like that. So this is negative 28 over 9 cube root of t, like that. And the question is asking us 8 seconds, right? And it said deceleration. D means negative. So we're expecting a negative answer here. So a of 8, let's plug 8 in there. What's the cube root of 8?
It's 2.
2. So the answer I get here is negative 6.2. And again, remember, AT is the slope of velocity versus time. What will be the unit?
Meters per second squared.
Yes, perfect. Meters per second squared. And it said the word deceleration. We're expecting a negative answer, and we got a negative answer as well. So this seems good. So that would be the final answer for this one. Cool?
Mm-hmm.
Let's look into something called optimization. Optimization is basically trying to maximize or minimize a certain parameter. So let's look at this question. Mathematically, this is very simple. But the tricky thing in optimization is getting to the equation bit. If you have an equation, usually what you do is you'd find the first derivative, you'd set it to 0, and you'd solve for x. That's it. That's the gist of an optimization problem. But the hardest thing is right here. This thing is not easy, especially the more complicated a function gets or the problem gets. If you can get to this level, this is easy. So let's see if we can get to that level. A farmer has 800 meters of fencing and wishes to enclose a rectangular field. On one side, the field is already against a country road. All right, so we have a rectangular field like this. And on one side, it doesn't matter which side, on one side, there's a road. And there's vehicles stuff like that. So the farmer only needs to fence these 3 sides. He doesn't have to fence the 4th side because the road is already fenced. How does the farmer determine the dimensions to achieve this goal? And what's the goal? The goal is to maximize the area. So let's write that down. The goal, the optimization problem, is to maximize the area of this rectangle. All right, cool. So how do we even start? So we need an equation for an area, right?
Mm-hmm.
We need an equation and we need to maximize this. So we need to find a prime and set it equal to 0. So this is what we need to do. All right. Let's say this is length. This would be length. This will be width. What is the perimeter of this rectangle in terms of L and W?
2L plus W.
2L plus W. So this is the amount of fencing we need to put up. How much fencing do we have?
800 meters.
So 2L plus W equals 800. Now let's solve for either W or L. W would be 800 minus 2L. Okay?
Mm-hmm.
Like that. Keep that in mind. I'm going to call this equation 1. What is the area of this rectangle in terms of L and W?
WL.
WL. But we know W is 800 minus 2L. So here's the thing. When you're trying to take the derivative, better be one parameter, one variable. If you have multiple variables like we do here, WL, it becomes a lot more complicated. We need to use techniques from another calculus topic called multivariable calculus, which is usually a second-year university course. So we're not going to get into that. We're going to try and keep this simple. So we don't want to be dealing with multiple dimensions here. I just want one variable. So I'm going to substitute W with what W is in terms of L. That way, I have only one variable I'm worried about. Like that. Let's open this bracket. Again, I'm going to write down increasing, decreasing degrees. So there you go. That's our area function. Our area function is that. We need to maximize the area. So we need to find, it's a quadratic, right? This thing, you agree? It's a quadratic, goes through 0, 0, because you can pull out an L. So it'll look something like this. We need to find what x value, for what length here, because our x value is length, what length will maximize our y value. So that's the goal. We basically need to find the vertex. To find the vertex of a quadratic, find the first derivative, set it equal to 0. That's A. What'll be A prime? What's the derivative of this function?
Negative 4L plus 800.
Yes. And now what we're doing is we found this. We found the slope function, and we know at the vertex, what's the slope?
It's
0.
0.
So set it as 0. Negative 4L equals negative 800. L is 200. Plug it here to find W. 800 minus 2 times 200. 800 minus 400, 400. So the width is 400. The length is 200. 4 times 2 is 8. 0, 0, 0, 0. That is the maximum area, 80,000 meters squared. And we're done with the problem. So the goal was to just find the vertex of this quadratic. You don't even need to use calculus. You could just use the normal, because since this one is opening downwards, you could definitely find the x-intercepts. Because the leading coefficient is negative, it's going to look like this. It definitely has two x-intercepts. You can find them, find the midpoint. You don't have to use calculus, but makes things way easier because you just solve this. Does that make sense?
Mm-hmm.
That's what they got as well, 80,000. Now this next question is tricky. I don't know if I have enough time to do this, but I'll just show you what this is. This is a very popular problem. The last one is also very popular. You might see it. You'll most definitely see it in your math class. This, again, this one is also very, very popular. I've seen this many times in many textbooks. So what's happened is that you have a rectangle. It's a sheet metal. Sheet metal just means a piece of metal sheet. Think of like a plywood, but not plywood, but in terms of like aluminum, stainless steel, carbon fiber if you really want, stuff like that. So this is measures 60 by 30. This is what we have. The goal is to turn this piece of 2D sheet into a three-dimensional box. So what we're gonna do is we're gonna cut a certain value here, x. On this side, we're also gonna call this x. We're gonna cut out the corners in all four sides, x, x, and these are all squares. The x's that we cut out are all squares. So as you can imagine, these don't exist anymore because we've cut them out, we've thrown them. So this is what your sheet metal looks like right now. And then in the next step, what we do is, you see this and this, we fold it inwards. We fold this inwards. They have a folded diagram. It's usually not that easy to see, but we take this, we pinch it, we move it this way. We take this, we move it this way. So eventually what you'll have is something like, I'm just going to steal their drawing, something like this. Remember, our length is 60, the original box anyways. Our width was 30. But now here's the hardest part. What's the height of this box? Turns out, remember this was x, right?
Mm-hmm.
And we flipped this onto the box itself. So the height will be this side length right here. What is this side length? Remember, this is a square. If that's x, what would this be?
X.
It'll also be x. So for this box, though, 60, we took away one x, we took away another x. The length is 60 minus 2x. For the width, it was 30. We took away this x, we took away this x. So the new width is 30 minus 2x, and that's the height. Therefore, your volume is 60 minus 2x, or 20x, 30 minus 20x times x. You agree with that?
Mm-hmm.
That's our volume function. What do we need to do to the volume function? Max or min? Max, right? So we need to find v prime, open this bracket, find v prime, set it to 0. I'm just gonna steal their open bracket thing because our values are the same. So when you open this bracket, this is what you get. This is still v. Let's find v prime. 12x squared minus 360x plus 1800. Let's set this equal to 0. It'll give us two different x. You have to use a quadratic formula. It'll give us two different x values. Now think about this. Only one of these x values is gonna be valid. If x were to be 23.7, would your width be positive or negative? Same thing here. If you replace this x and this x with 23.7, do you think we get a positive value or a negative value? We'd get a, no, we'd get a negative value. Look at this. So this is going to be 30 minus 600 something. It'll give us a negative value. Width cannot be negative. Neither can length. Length would also be negative if you were to use this x value. So what we do is we ignore this x value. This is invalid because this will give us a negative width and a negative length. What about this one? This one, okay, I know what I messed up. These are not 20, these are 2x's. But the idea is the same. This was 2x, this was 2x. 23.7 here would give you a negative value. I think length is still good though. Yeah, 60 minus 47 should be good. But the width would be negative, so this value is moot. We can't use it. So this must be our final answer. And that's the end of this question. All right, let's call it there. We'll pick this up next week right here.
Okay. Thank you.
See ya.